Hello, my name is Roman Bartak, and this is a joint work with Jindřich Vodrážka and Jiří Švancara. I'm going to talk about solving a multi-agent path-finding problem, which is a problem of finding collision-free paths for a set of agents moving on a graph. At each time, either the agents can move to a neighboring node, or it can stay in the node where is it right now. At the end, each agent should be in its destination, and there should be no collisions between the agents. There are several types of collisions. Some of them are derived from physical properties of agents, meaning that two agents cannot be at the same time at the same location, like the edge or vertex conflict. Other type of collisions or conflicts are just virtual conflicts, like the following conflicts. Agents cannot follow each other, or cycle conflict. Agents cannot move on a cycle. A special type of a cycle is swapping, where agents swap positions using a joint arm. In this talk, we are focusing on modeling the multi-agent path-finding as a planning problem, specifically on modeling the various type of collisions. You may believe that modeling the problem is quite simple. We just need to encode the move action using preconditions and effects. This is an example of encoding in PDDL language. Then we obtain a sequential plan of move actions, and we can group these actions into parallel steps by assuming actions of different agents not sharing the same node in the same step. Like in this case, where color describes the move actions of a specific agent, we can split the sequence of move actions into subsequences, and these subsequences are for different agents not sharing the node, so they can be done in a single parallel step. So in this model called pebble motion model, we naturally encode edge, vertex, and swapping conflicts. If we want to allow them, we just need to modify precondition of the move action. But what about the following conflict? Following conflict is not allowed, but if we do parallelization, where we allow actions that are describing the train in the same parallel step, we may allow trains in the model. But this is not possible for cycles, because in cycles, the actions need really to be run in parallel. Fortunately, we can model cycle by splitting the original move actions to two actions where agent first moves to the arc and then it moves from the arc to the other node. Simple, right? But this is not a correct model because it may lead to plans that are not invalid, like in this one. The red agent moves in the arc and the green and black agents are using the end nodes to reach their destinations before the red agent finishes its move. So we need a more advanced model. We call it a sequential model where we combine action splitting with node freezing. Agent freezes the node where it wants to go. This is not possible for cycles because that node is occupied. So we need an additional mechanism for cycles where agent is requiring the node from another agent, which means that it's actually pushing the agent away from the node. Like in this example, where the black agent requires the node from the blue agent, which then requires the node from the red agent, which requires the node from the green agent, and finally the green agent can move to an empty node. But this node can be used by other agents in the meantime. So we need to lock these agents, so only these agents can use these nodes at the same time. It's a quite complicated model, but it describes the idea that we may force the agent to do the action. So we propose a different model that we call a layered model, where we use a token passing mechanism to force agents to do actions. And the agent which is assigned to the token can do the action. We still use action splitting. So in the first round, each agent moves to the edge or stays in the node. And in the second round, the agent moves from the edge to the next node or stays in the node where is it right now. So it's easy to parallelize a sequential plane obtained using this model because this plane consists of a sequence of layers and each layer describes opening and closing actions for the agents. So the multi-agent path planning can be solved easily using these parallel steps. So how do these models compare? We use the problems from Moving AI library and we use the FF Planner to solve them. For comparison, we use the PyCat solver as an ad hoc solver for multi-agent pathfinding. And this is the result, the number of problems solved within a given time. Surprisingly, the Pebble model is very good. It's much better than the ad hoc solver. Sequential model is not that good, but the layered model is still comparable to ad hoc solver. So in this talk, we present how to model multi-agent pathfinding as a planning problem. We believe these models are useful by themselves by proposing techniques like action splitting, node freezing, and token passing. We use a very simple mechanism to parallelize a sequential plan. So the open problem is if we can do better parallelization to obtain plans with smaller make span. And that's it. Thank you for your attention.